Here we are going to talk about the relationship of the time varying fields in electromagnetic waves. For this, we consider that the electromagnetic wave is propagated along positive z direction, that is towards unit vector z, and the time varying fields are electric field and magnetic field. So here we consider that the electric field has x component, that is the electric field is directed towards positive direction of x. So here we consider a wave propagate along unit vector z and electric field has x component that is directed towards unit vector x and is given by E vector suffix s equals to E suffix x as function of z unit vector z. Since we know that the wave is propagated towards positive z direction, so the electric field is a function of z but it is directed towards unit vector x. Now from Helmholtz equation, that is within bracket del square minus gamma square into E.S equals to 0. Here we consider a magnitude of electric field E suffix s vector. So after opening the bracket we get del square E suffix s minus gamma square E suffix s equals to 0. So from here the first term is del square of E suffix s, and this is given by in terms of all the three coordinates, that is x, y and z, and given as del square E suffix xs function of z upon del x square plus del square E suffix xs function of z upon del y square plus del square exs function of z upon del z square minus gamma square E suffix xs function of z equals to 0. Here the magnitude of electric field E vector is E suffix xs function of z. As in electromagnetic field, the electric field is time varying field and it is a function of z only, so the first two term is cancelled, that is with respect to x and with respect to y, because the electromagnetic fields is propagate along z direction. So the electric field is a function of z, so the del square of magnitude of E vector is with respect to z only. So the first two term is cancelled here and we get only d square upon dz square into E suffix xs function of z minus gamma square E suffix xs function of z equals to 0. So here we take a magnitude of E as a common and we get d square upon dz square minus gamma square into exs function of z equals to 0, and this is called a homogeneous differential equation. It is of second order. The solution of this second order differential equation, that is a homogeneous differential equation, is given as two functions. The first function is for forward propagation and second function is for backward propagation. In forward propagation we have exponent term, that is e to power minus gamma z, here minus sign is there, and in backward propagation we have e to power plus gamma z, and there is a magnitude for forward propagation, that is E naught, and for backward it is E naught dash. So here E naught and E naught dash are the constant which describe the amplitude for forward propagation and backward propagation. Now as we take electric field as a function of z, that is displacement, and this field must be finite at infinity, means as wave propagate along positive z direction and as it reaches to infinity, then its value must be some finite value. For this we put z equals to infinity on both the terms, so we get the first term, that is e to power minus infinity is 0, but in the second term we get e to power infinity which is undefined. So we take only the first term and we get equation, that is e suffix xs function of z equals to E naught e to power minus gamma z. So this is the magnitude of the electric field in any electromagnetic wave that propagate towards positive direction of z, so that it is a function of z only. Now this is a magnitude of electric field, that is a function of z, that is a displacement, z is the displacement. Now if we introduce a time that the electric field as a function of displacement as well as time, we introduce a time factor. For this we multiply the equation by a term that is called e to power j omega t. After multiplying e to power j omega t, we take a real part. After real part, we get a instantaneous value of electric field, that is a function of displacement z and time t. So the equation becomes the real part of within bracket e suffix x s vector function of z into e to power j omega t unit vector x. Now in place of vector e, we can write E naught e to power minus gamma z. Here E naught is the amplitude of electric field in case of forward propagation, and there is a exponent term, that is a time factor term, that is e to power j omega t. Now we put the value of gamma, that is alpha plus j beta, and open the bracket according to real part and imaginary part. So the exponent becomes real part of within bracket E naught e to power minus alpha z into e to power j within bracket omega t minus beta z unit vector x. So this is the equation of electric field in case of electromagnetic waves, and this electric field is a function of displacement z and time t, and called as instantaneous value of electric field E. Now as we know that the electromagnetic wave travel towards positive z direction and the electric field is directed towards x direction, so the magnetic field, that is the time varying magnetic field, is directed towards y direction, and this electromagnetic wave is called transverse electromagnetic wave. Here electric field and magnetic fields are perpendicular to each other and also perpendicular to the direction of propagation. Now we obtain the intrinsic impedance of the wave. When electromagnetic waves are propagated from source to destination, it has some characteristic. That characteristic is called intrinsic impedance of the wave. For this we consider a electric field, that is a sinusoidal one, denoted by E suffix s, and it has a direction towards x direction, and this electric field is function of z because the electromagnetic waves is propagate towards z direction, and the magnitude of this electric field is E naught e to power minus gamma z, that is a forward propagation. To obtain the finite value of electric field, we take a forward term, that is called E naught e to power minus gamma z. Now to obtain the intrinsic impedance of the wave, that is a characteristic of the electromagnetic wave, we take a curl of electric field. So the curl of electric field is del cross E vector, and it is equals to, in matrix form, the first row is for unit vectors, the second row is for del upon del x, del upon del y, del upon del z, and the third row is for the component of E. And here the electric field is directed towards x direction, so it has only x component, that is E suffix xs function of z. Now after taking a curl of E vector, we get two components. First is towards y direction and second is towards z direction. And as the electromagnetic wave propagate towards z direction, so the electric field is a function of z and varies along z direction. So we restrict electric field variation only with z direction. So the second term get neglected. Now the curl of E vector is equals to del upon z, del z E suffix xs function of z unit vector y. And we know that this is the magnitude of electric field E, and it is E naught e to power minus gamma z. That is a forward part. Now the left side is curl of E vector, and we know that the curl of E vector is equals to minus j omega mu Hs vector. This is the Maxwell's equation for the time varying fields that is obtained in Faraday's law. So the left side is minus j omega mu H suffix s vector. Now we take a magnitude on both the sides. Left side, the magnitude is j omega mu h naught. Here h naught is the magnitude of Hs vector. And in the right side, after taking a magnitude part, we get E naught into gamma, because we know that the magnitude of e to power minus gamma z is 1. So we get E naught into gamma. Minus is cancelled here. We take only the magnitude on both the side. So from here we get a relationship between the magnitude of electric field E naught and the magnitude of magnetic field H naught. So the relation is H naught equals to gamma upon j omega mu into E naught. From here we obtain the ratio, that is E naught upon H naught, and this is equals to j omega mu upon gamma. This ratio, that is the ratio of magnitude of electric field and magnetic field, is called the intrinsic impedance of the wave, and it is calculated in ohms. Since here we see that the intrinsic impedance is equals to j omega mu upon gamma. This is a imaginary part. So we can say that the intrinsic impedance is complex quantity. It has a zero real part, and imaginary part is omega mu upon gamma. Now as we obtain the intrinsic impedance in terms of complex quantity, so it has a magnitude and phase. To obtain the magnitude and phase of the intrinsic impedance eta, we use a gamma square, that is a propagation constant, that is obtained in case of Helmholtz equation. The propagation constant gamma square equals to j omega mu within brackets sigma plus j omega epsilon. So the gamma is equals to under root of j omega mu within brackets sigma plus j omega epsilon. Now we take j omega mu outside the square brackets. For this we have to divide by j omega mu. So the gamma is equals to j omega mu under root of sigma plus j omega epsilon upon j omega mu. And from here we take a ratio, that is j omega mu upon gamma, and this ratio is called the intrinsic impedance of the electromagnetic wave, and its value is under root of j omega mu upon sigma plus j omega epsilon, and this is a complex quantity. This intrinsic impedance denoted by eta have a magnitude and phase. The magnitude is denoted by mod of eta, and the angle, that is the phase, is denoted by theta suffix eta. And here the intrinsic impedance eta can be written as under root mu upon epsilon upon 1 plus sigma upon j omega epsilon. This is obtained after taking a common j omega epsilon in the denominator. So from here we get a magnitude of eta, which is in the numerator, that is under root mu upon epsilon, and in denominator it is 1 plus sigma upon mu epsilon to power 2 and whole to power 1 by 4. This is because the eta is a square root term, and after taking a magnitude we again take a square root, so we get a power 1 by 4 in the denominator. And to get the phase, that is theta suffix eta, we take a denominator term, and in denominator we have sigma upon omega epsilon. So the angle is obtained by tan to theta suffix eta, that is equals to sigma upon mu epsilon. Here there is 2 into theta suffix eta. This is because here the denominator has a power of 1 upon 4, and here the value of angle theta suffix eta is from 0 to 45 degree. So here we introduce a characteristic of the electromagnetic wave, that is called intrinsic impedance eta. And as we know that the electric field in electromagnetic wave is a function of displacement z and time t, and it is written as electric field E vector, that is a time varying field, equals to E naught e to power minus alpha z cos within bracket omega t minus beta z unit vector x. This is obtained after multiplying by a time factor and taking a real part. Now, as we know that in electromagnetic waves the electric field is directed towards x-axis and the magnetic field is directed towards y-axis, and the direction of propagation of electromagnetic wave is towards positive z direction. So that the electric field, that is H vector, that is a function of z and time t, is obtained as real part of h naught e to power minus alpha z e to power j within bracket omega t minus beta z unit vector y. The direction of H vector is unit vector y, that is towards positive y direction. And here we know that the intrinsic impedance is the ratio of E naught upon H naught. So from here the H naught is equals to E naught upon eta, that is the magnitude of magnetic field H vector. After putting the value of H naught, we get H vector function of z and t equals to E naught upon eta e to power minus alpha z cos within bracket omega t minus beta z unit vector y. Now we know that the intrinsic impedance is complex quantity. It has magnitude and phase. So we write eta equals to mod of eta e to power j theta suffix eta. Now here there is an angle, so we take it with the phase, and equation becomes H vector equals to E naught upon mod eta e to power minus alpha z cos within bracket omega t minus beta z minus theta suffix eta unit vector y. Here in case of magnetic field there is a phase, that is theta suffix eta, that is obtained from intrinsic impedance. So from here, after comparing electric field and magnetic field, that is a time varying field, we find that the electric field leads the magnetic field, or the magnetic field lags electric field by phase theta suffix eta. So as the wave propagates along unit vector z, it decreases or attenuates in amplitude by a factor of e to power minus alpha z. As we see here, the amplitude of electric field is E naught, that is multiplying by e to power minus alpha z. Here the amplitude E naught is decreases or attenuate by a factor of e to power minus alpha z. Similarly, the magnitude of H vector, that is E naught upon mod of eta, also decreases or attenuate by the factor e to power minus alpha z. So from here the alpha is called the attenuation constant or attenuation coefficient of the medium. It measures the spatial rate of decay of the wave in the medium. Spatial rate of decay means the space rate of decay, that is with respect to displacement z, and its unit is Napier's per meter or decibels per meter. So here 1 ampere is equals to 20 log base 10 into E, and it is equals to in decibel value, which is 8.686 decibel. Here we note one point. When we say that fraction of 1 ampere, it means that it is reduced by a value of e to power minus 1 of the original value. Similarly, if we say that increase in 1 ampere, which means that there is an increase by a factor of E. So from here we conclude that the electric field and magnetic field, that is the time varying fields, are out of phase by theta suffix eta, that is obtained because of intrinsic impedance of the electromagnetic wave. And we see that the electric field leads magnetic field, or the magnetic field lags electric field by theta suffix eta.